On June 23rd, a netizen from Shandong steel pipe company posted a video on Douyin saying that a German client had entrusted them with processing steel pipes. After the processing, the waste materials and slag had to be taken back. They finally understood why the German products are so expensive. The netizen then commented, "China's manufacturing still has a long way to go." In the comments, one netizen wrote something that resonated with many. "The quality of Chinese metals compared to German metals is like day and night. There's a huge difference in quality. Chinese metals are the worst, so Germany takes back all the leftover slag, ensuring China doesn't steal metal technology." In 2018, the US-China trade war broke out, and the Chinese tech companies faced sanctions. 7 years later, how are the 35 critical technologies that China once called its choke points progressing? Has China broke through the blockade, or is it still held back? In this video, we will systematically review the current status of these 35 technologies and analyze the challenges and roots of the core tech issues China faces. The choke point technologies refer to key technologies that China depends on imports for but struggles to develop independently. In April 2018, China's Science and Technology Daily first published a list of these 35 technologies. They share a common feature. They're fundamental to modern industry, and blocking them would have a devastating impact on the entire industrial chain. These 35 technologies can be roughly divided into 4 categories. 1. Core components. Chips, aircraft engine nacelles, tactile sensors, mobile phone RF components, LiDAR, high-end capacitors and resistors, milling cutters, high-pressure plunger pumps, tunneling machine bearings, underwater connectors, high-end welding power supplies, medical imaging components, etc. 2. Key basic materials, ITO targets, aviation steel, high-end bearing steel, photoresist, key materials for fuel cells, lithium battery separators, ultra-precision polishing processes, epoxy resins, high-strength stainless steel, etc. 3. Advanced basic processes, photolithography machines, vacuum deposition machines, core industrial software, aerospace design software, etc. 4. Industry technology foundations, operating systems, heavy-duty gas turbines, airworthiness standards, core algorithms, high-pressure common rail systems, transmission electron microscopes, database management systems, scanning electron microscopes, etc. Lithography machine, an insurmountable technological barrier. Photolithography machines are the core equipment for chip manufacturing. Nearly all high-end photolithography machines are produced by ASML in the Netherlands, and their key component, extreme ultraviolet lenses, relies on the optical technology of German company Zeiss. Even if ASML were to release its design blueprints, Chinese manufacturers would still find it difficult to replicate. The reason lies not just in the equipment, but also in the materials, processes, and systematic accumulation of experience. General Manager of SMEE, He Rongming, told Science and Technology Daily, "For the same lens, if different workers grind it, the smoothness can differ by 10 times. He observed that in Germany, workers polishing lenses in one company had been in the same position for 3 generations. Investment in chips, like most of China's high-tech investments, follows a shortcut approach, but ultimately results in low-level repeated investments, leading to low-end overproduction. This is almost a universal story." In the past decade, the Chinese government has strongly promoted an independent chip strategy, investing around 3 trillion yuan, leading to the establishment of 60,000 chip companies. Various domestic alternative slogans flooded the market, creating a massive chip movement. However, reality has been unforgiving. The so-called chip breakthroughs were more about political tasks and promotional tools rather than actual technological achievements. The result is that chips were never produced, but subsidies were completely exploited. Currently, SMIC's most advanced process is still at 7 nanometers, while TSMC, Samsung, and Intel are set to offer 2 nanometer processes to customers in the next 12 to 24 months. This will further widen the technological gap between China and the rest of the world by at least 3 generations. Aerospace engines, a dual challenge of materials and technology. Aerospace engines are often called the crown jewel of the industry. The short nacelle component within them bears extreme temperatures and pressure, requiring very high standards for both materials and manufacturing processes. GE Aviation in the United States is the only company in the world that has composite fan blades and sealing systems. The design, materials, testing, and certification of just its composite fan blades took 10 to 15 years, involving a huge team and generations of knowledge accumulation. This process requires great dedication and resolve. While China has models like the WS-10, there is still a significant gap with the West in terms of service life, reliability, and fuel efficiency. Commercial engines have even higher thresholds, and the C919 large passenger aircraft still depends on imported engines. Chief designer Gu Chunwei of China's heavy-duty gas turbines said that its three key components require a lot of fundamental research support and long-term testing and validation. These components are the compressor, combustion chamber, and turbine. Even with money, without long-term accumulation of knowledge, you wouldn't know where to start. He explained that, for example, even with precise work on turbine blades, the material still has a limited lifespan. How do you prove that it can run safely for 50,000 hours? Testing materials under extreme conditions for 50,000 continuous hours is essential. This means huge investments, a massive amount of time, and the collection of vast amounts of data. Every step must be done personally, or else you won't understand the reasons behind it. Another thing the Chinese Communist Party can't produce, despite its spending, is carbon fiber composite fan blades used in engine casings to help airplanes land safely. The Japanese company, Nikiso Group, holds 90% of the market share. Takeshi Iwaoka, head of Nikiso's aerospace department, dismissed the threat from China. He told the Financial Times that competitors had been trying to catch up for 40 years but had never succeeded. He says, the process involves laminated molding into a complex shape, which is quite a sophisticated manufacturing method. We have a lot of proprietary know-how when it comes to shaping and forming this kind of product, and other companies just can't easily replicate it. He pointed out that the Japanese government is stepping up efforts to protect its core technologies in aerospace and other strategic fields to prevent them from being targeted by industrial espionage. High-end steel and bearings, the weakness in basic industries. China is the largest steel producer in the world, but it still heavily relies on imports for high-end steel. Key materials like aerospace-grade steel, pen-tip steel, razor blade steel, bearing steel, and panel steel are still not fully domestically produced. High-end steel also involves both materials and processes, and it can't be achieved through sheer manpower alone. Take bearings, for example. China's high-speed rail, wind power, and domestic industries still rely on imports for high-end bearings from Japan or Germany. Domestic bearings still lag far behind in terms of reliability, lifespan, and precision. Industry experts point out that China's bearing industry is at least 20 to 30 years behind Europe, the US, and Japan in areas like heat treatment, theoretical design, and precision machining. Now let's take a look at how Chinese auto repair workers complain about the steel and bearings made in China.
Check out American steel. Take Ford's Raptor, for example. It's light as a feather and top-notch quality. Now, this one's from Korea. I'm telling you, it's been over 20 years and not a speck of rust. Pure perfection. Then there's China stuff. Look at these Chinese screws. You see them? Compare them to Japan screws. Man, these are so light. You hear that snap? It just pops off on its own. Korea's got some solid stuff too. And Japan? Oh, let me tell you, their parts are crazy light. This one's galvanized. You couldn't make it rust if you tried. Now, check out China's new drive shaft. Rusted, right? Not just here, but there too. You see? Even Wei Jiangjun, Great Wall CEO, called it a matter of conscience. Germany's stuff? Light as can be. Everything's light except China's. Their steel's heavy, man. That's Chinese made for you. Just talking about Chinese products gives me a headache. Can't even make a decent shaft, you know?
As for bearings, Liu Qianqun, who worked for a leading bearing company in China for many years, says there are four major differences compared to foreign companies. First, the heat treatment process. Japan is the best in fine heat treatment, and Germany excels in high-speed forging. Second, the gap in theoretical analysis is too big, including data for theoretical design and application data. Third, there's a big difference in error-proofing measures during grinding, which results in Japanese bearings having a reliability rate of over 98%, while the best Chinese bearings are around 96%. Fourth, Chinese bearing companies are large and all-encompassing, while those in Europe, the US, and Japan are small and precise. Chinese media reports that domestic tunneling machine main shafts have made breakthroughs, but Liu Qianqun believes that they still haven't fully replaced imports, with a significant gap in service life. He says that if the supply chain in these choke point industries are interrupted, many sectors in China would stop immediately. In terms of bearings, industries like aircraft, high-speed rail, steel mills, metallurgy, and most military sectors would basically be paralyzed. While there has been progress in localization in recent years, it's really just the difference between being usable and being good. It's also the difference in service life, and this is the difference in reliability. As for pen-tip steel, China has more than 3,000 pen manufacturing companies with over 200,000 employees, producing more than 40 billion pens annually. However, even though they produce 7 parts for ballpoint pen refills, China still imports 170 million of them annually from Japan. Pen-tip steel, which is the ball in the pen, was still 80% imported as of 2021. As a special kind of steel, pen-tip steel production requires more than 20 processes. The precision for the surface of the ball seat body needs to reach the micron level, and the precision for the 5 ink guiding grooves inside is even stricter. The internal hole diameter at the very top of the ball seat body must be strictly controlled between 0.3 to 0.4 millimeters, tens of times thinner than a hair. These requirements make pen-tip steel production incredibly complex. According to China's customs data, in 2023, China imported more than $28 million worth of ballpoint pen refills, 2.5 times more than the import amount in 2017. Similar to pen-tip steel, stainless steel used for razors has long relied on imports. The thickness of razor blades does not exceed 1 millimeter, and the edge reaches the nanoscale. Any millimeter-sized debris can cause the blade to chip or even rust, affecting the initial sharpness and greatly reducing the comfort of the product. This requires the raw materials to have ultra-high purity, processing toughness, and strong corrosion resistance. In addition, razor steel has a high carbon content, and controlling the process is extremely difficult. Issues such as steel leakage, broken strips, and edge cracking constantly challenge technology in production. China's high-end razor stainless steel materials have always relied on imports, with over 2,000 tons of ultra-high carbon Martin stainless steel being imported annually from abroad. Moreover, in the field of aerospace steel, which is used for landing gear, China has a significant gap compared to the US and Japan. China falls behind in areas such as advanced rolling, cooling, and heat treatment technologies for super-strong aerospace steel. China's annual market gap for high-temperature alloys used in large military and civil aircraft landing gears is nearly 10,000 tons. Su Jie from the Special Steel Research Institute of China's Iron and Steel Research Institute says that most of China's aerospace materials are still from the 1960s and 70s, and China is still in the imitative stage, trying to catch up with the world's leading technology. High-end machine tools and industrial software, the absence of the mother of industry. High-end CNC machine tools, known as the mother machines of industry, are the foundation of manufacturing. China proposed in 2015 that it would reduce foreign dependence, but the domestic manufacturing rate is still under 10%. The key issue is that not only is hardware difficult to break through, but core control software has been monopolized by companies like Germany's Siemens and Japan's Fanuc. Even though many Chinese companies have domestic alternatives, they still need to purchase foreign products for one simple reason: stability and reliability. Ai Rongwei, the executive director of the Taiwan Inspiration Association, said that from start to finish, the Chinese Communist Party is politically driven, and government leaders are all focused on performance to climb upward. The CCP respects power, not professional knowledge or creativity. No amount of people or technical equipment will help. The culture and creativity of private enterprises are sometimes seen as a challenge to the CCP's authority. He said that if this system doesn't change, no one will want to work hard for the country, because it's not people-centered. In this system, blue-collar workers are seen as people without talent, and their social status and income are not competitive to Germany or Japan. The technological breakthroughs needed for frontline production are often unable to attract enough students to technical schools. Many researchers, under pressure from government assessments, are more focused on publishing papers, turning into paper production machines. In simple terms, the root cause lies in the system and culture. First, research tends to focus on short-term performance, neglecting basic research and long-term accumulation. Second, blue-collar workers are viewed as lower status, lacking a culture of craftsmanship and technical inheritance. Third, innovation in private enterprises is limited, and the institutional environment is not conducive to technological breakthroughs. Fourth, there's insufficient investment in foundational disciplines like material science, and a lack of interdisciplinary integration. The strategic goal of the US and its allies is not to make China regress, but to freeze its technological development. As long as China's key technologies are locked at the level of the late 1910s, the West can continue advancing, and the gap will naturally widen. This technological gap not only affects economic competition, but will also create a strategic suppression effect in fields like military and aerospace. According to a recent report from Harvard University, the US continues to lead China in key technology areas, including artificial intelligence, biotechnology, semiconductors, space, and quantum technologies. The report found that while China is far behind the US in all key technological areas, it remains competitive and is steadily closing the gap. However, once China's global expansion and ambitions to challenge the world order are recognized, the US began cutting off choke point technologies, which will affect the development of Chinese enterprises and even its economy. This scenario played out in 2018, when ZTE and Huawei were banned from selling chips, and the companies immediately faced crises. In April of this year, China imposed an export ban on rare earths to the US, and the Trump administration responded by cutting off the supply of aircraft engines. Su Ziyun, director of the Strategic and Resources Department at Taiwan's National Defense Security Research Institute, told foreign media that the U.S. strategy is to freeze Chinese technology at its current state. Whether it's high-speed, high-temperature turbine blades or turbine bearings, they can be frozen at the standards of the late 2010s. The most critical area is advanced chips. Although China's military engines, such as the WS-10, can still be used, others can run for 10,000 hours, while China's engines may fail after just 2,000 hours. Commercial aircraft engines are even more stringent, and while China says it won't kneel, the C919 still can't take off. He said, the Western democratic countries continue to advance, which allows them to further widen the gap. This technological gap, while maintaining economic competitive in daily life, will naturally create alternative deterrence effects in the military, since military technology still relies on civilian technological support. If all this is blocked, China's economy and military power will stagnate, creating all these effects. Although China has made breakthroughs in certain fields, such as electric vehicles, some RF components, and lithium battery materials, it still faces severe challenges in broader and more foundational areas. Technological independence is not a sprint, it's a marathon. It requires institutional guarantees, cultural support, talent accumulation, and long-term investment. In a closed, vertical, and highly metrics-driven system, any national-level technology plan can eventually transform into a waste of resources, a misdirection of focus, and institutional inefficiency. Real technological breakthroughs require market mechanisms, social openness, freedom of speech, and protection of property rights, and these are precisely the things that the CCP cannot tolerate.